Task 444, design of a switching position for a flying capacitor converter, medium voltage and balanced current static compensator. This is a collaborative project between the Electric Power Research Institute and the University of Arkansas at Fayetteville. My name is Juan Carlos Balda. I'm the PI at the University of Arkansas. Vincent, John, and A.Rahouma are the two doctoral students working in this project, and Adapa is involved from the EPRI side. This presentation will address the project objectives, the topology, power stage construction, and preliminary experimental results of the medium voltage and balanced current static compensator. Project objective is to design a three-phase medium voltage and balanced current static compensator that connects directly to 13.8 kV without using step-up transformers, balances the upstream currents flowing into the substation, complement the work of shunt capacitor banks by providing reactive power, and make use of silicon carbide MOSFET. This slide presents a potential application for the static compensator. We are assuming a substation having a power factor 0.8 lagging and compensated, and the largest imbalance between two phases is 15%. There the figure shows at the top the substation, at the bottom the loads, and towards the left you have the connection of the medium voltage and balanced current static compensator. What you see there, the loads are imbalanced. On the top left you have the imbalanced current static compensator injecting currents to compensate the imbalanced loads, resulting in the substation currents being balanced. Why flying capacitor converters? Well, an important figure of merit or driving factor was the high power density. The sizes of the passive components in a flying capacitor converter are inversely proportional to the switching frequency. Other topologies that module a multi-level converter are inversely proportional to the fundamental frequency, the system frequency of 60 Hz. We think that we can scale up to higher powers and voltages. We have less losses than other converters, and for certain PWM schemes, the submodule capacitor voltage can be self-balanced. This slide presents a summary of the topology. On the top left is the 11-level flying capacitor converter. Each switching position is in 2.4 kV. The DC bus on the left is plus minus 12 volts. And then you got 9 flying capacitors, and those are the voltage that they are subjected to. We have 60 switching positions, and we will explain in the next slide why we have 120 discrete packages. The effective switching frequency for this type of converter is the number of levels minus 1 times the switching frequency of a switching position. So 11 minus 1 is 10. The switching frequency of a switching position is 10 kHz, so what we have is 100 kHz. There you have the LCL filter specified below. On the other table on the right hand side, you have the flying capacitors, 160 nanofarad for every 33 kVA if we want to get a 10% voltage ripple. The flying capacitor positions are 27, 9 per phase times 3, and the DC bus capacitance is 80 microfarad if we want to get 5% voltage ripple, or 91 microfarad per 33 kVA if we want to get 1% voltage ripple. Why 120 discrete packages? Because we wanted, for a 2.4 kV voltage applied to each switching position, we will need to use 3.3 kV devices. Unfortunately, the budget in this project didn't allow to buy all 30 half-bridge modules, and so we decided to use two series connected 1.7 kV silicon carbon MOSFET. They are connected here. So when you use series connected devices, you have to balance the voltage across them during dynamic and static conditions. Another issue that we solved is that the common mode voltage isolation issue. Basically, we designed a circuit based on resonant principle that uses the voltage across the switch in the off position to charge a capacitor that will provide the power supply to the gate driver. So the only thing that we need to connect to the switching position are 4 fiber optics that are carrying control signals and also fault triggering protection signal. Here is on the left the SolidWorks rendition. That's what we normally do before we build it. Here on the right is built. Here are the two silicon carbon MOSFET rated 1.7 kV. Here we have the controller module. We don't have a picture but this is a SolidWorks rendition. Basically, we have a computer that talks to a DSP, and the DSP provides all the control, process all the control signals and provides the signals for FPGA, which are the ones that produce the 60 PWM signals, and also a second FPGA handling fault triggering. Here on the left, once again, is a SolidWorks rendition. Here is the prototype built at the National Center for Reliable Electric Power Transmission. Here we have a capacitor, the DC bus. The blue is the flying capacitors, and here we have the switching positions. And here is the prototype ready to complete testing. Here are some examples showing the operation of the voltage balancing circuitry. We selected that S1 turns on 250 nanoseconds before S2, so the voltage across S2 should raise to the DC bus, and in this particular case should cause destruction of this device because we are applying 2.4 kilovolt. So here in red you have the DC bus. This is the low current, and you could see that the voltage across the switch S2 remains within its safe operating area. And then finally, basically, we have here both devices S1 and S2 turn on. So the balancing circuitry works well. Here what we have is the self-power voltage waveform for the gate driver. These signals represent the two capacitors providing the voltage to the gate driver, and in blue is the current from the resonant inductor. Here we have the current. We have an application for a 3-level open loop testing where we are injecting current to the grid at unity power factor. So in blue is the current, red is the voltage. So here we have another applications where we show basically the process of DC bus charging, stabilization of the capacitor, flying capacitor voltages, and then gate synchronization. So this part is where we are charging the bus. Here we have current flowing because of the stabilization of the flying capacitor voltage, and here we are connecting to the grid, and here we turn it off. So in summary, we have developed VHDL modules for the FPGA. We have completed that work. We have developed startup routines and control algorithms. First, they were tested with HIL simulations. They were also tested under the 2 and 3 level prototypes. Then we developed test plans for the encrypt facility because we are going to be testing at 13.8 or synchronizing to a 13.8 kV grid and 24 volt. And then we have developed more plans for testing. We have fabricated the medium voltage and balanced current prototype. and we start the system debugging and testing at Encrypt. Has started.